Hello.
Hey, Bastian. Likewise. All systems operational. Thanks. Okay, welcome everyone. Now we should have the right slide check up and running. So let's get started. So welcome. This is the Think to Think Research Group interim meeting. My name is Ari Keränen and my co-chair Karsten Borman also. Quick reminder about the Notewell. So if all goes as planned, you are being recorded. Also remember to be nice, respectful, professional with each other, and as usual, the IPR guidelines of the IETF apply. There's more information about the Notewell in the following slides regarding IPR, audio and video recordings, and privacy and code of conduct. As usual, if you have any questions, please check out the RFCs or ask us chairs. More than happy to help here. Also, very quick reminder of the goals of the IETF. So here we focus on the long-term research issues related to the internet. So whereas the IETF focus on short-term is on engineering. So this group is more about the research, whereas IETF is about the standards development. However, we do work very closely with the IETF. For example, on more towards the applications in the core working group, where we look at protocol engineering of RESTful environments, or at the ASDF working group, where it's more about engineering format for IoT model convergence. And also on the operations area, there's the IoT Ops working group has a lot of discussion on operational issues, just to name a few working groups that are very relevant for the including RG work on the IETF side. Quick note on admin things. So we have, as usual, note-taking happening at the notes.ietf.org. You have a link here, but also in the meeting materials. I will be taking notes, but anyone feel free to chime in. More than happy to have your help on taking the notes. There's a mailing list. As always, if you haven't already subscribed to the mailing list, please do so. We always notify of relevant activities such as new meetings on the list. So that's where you get the best information. And as usual, we have a GitHub repository where you find the latest agenda and meeting logistics. A couple of words on the upcoming meetings and activities. So there is a plan to have so face-to-face at the IETF in Montreal. There is a hackathon planned on Saturday and Sunday. We haven't yet decided if there's going to be Think to Think RG focus hackathon there. So if you are joining the Montreal meeting and you would be interested in a hackathon, please do give a shout out either here or on the chat or over email. We'd be very happy to hear if we should have hackathon activities. We have had typical, for example, together with the ASDF working group around SDF, but we could also look at the other topics that are in the scope of the T2TRG. Also, we do have, while we don't have a summary meeting planned, we do have a side meeting planned for the Montreal meeting. So on Monday, November 3rd, 8 o'clock local time, 1300 UTC in the McGill room. And there's also already a repository for that side meeting. Still a bit open on the agenda, but probably continuing, for example, the discussions from this meeting would make a lot of sense among with everyone who's planning to be on site, but also will have a remote participation available. Regarding online meetings, as discussed in the previous meeting, we're also thinking about having next interim on the AI agent topics, following up on the discussions we had at the Madrid IETF meeting. But this will be after the IETF, maybe November, December, perhaps January timeframe. We'll have to look at the details on that. Yes. Sorry, this meeting seems to be a bit slow changing slides today. So here's the agenda for today. We are right now in the intro section. After the introduction, we will have Meron talk about sandboxing the sensor, how WebAssembly could be the future of programming for things. Follow that, Carolina will be presenting composing real-world smart control systems for container challenges and opportunities, following up on the presentations that we had in the previous IETF, but going more towards this composable code topic of today. And finally, we have Bastian presenting multi-tenant microcontrollers using WebAssembly-based containerization, showing how, for example, TinyML could be enabled with WebAssembly. And then we have a quite sizable block reserved simply for discussion. So we would, of course, have discussion during the meetings, but then more discussion around the topic in general towards the end of the meeting, before we finally wrap up in less than 2 hours. Any questions or comments on the agenda? Okay, in that case, I hand over to Karsten, give you a bit of introduction for the composable code. And Karsten should have their slide control now too.
Yeah, thank you. So the sun is shining in my face right now. Interesting. Yeah, good afternoon. Welcome to the T2TRG meeting from my side as well. And I just wanted to give the 2-minute introduction to the subject we are talking about. We already talked about this in meetings before. So for instance, we had a kind of keynote by Carolina on the IETF 123 meeting. It took us a while to come up with this term composable code, which may not be the lasting term we use for this, but for the moment, I think it's a quite useful term because it acknowledges that when we talk about things that communicate with each other, the code on those things will come from various places. And of course, today we install all kinds of operating systems and libraries and whatever, compile them together into one image that is then loaded on device, usually flashed on the device, and is totally fixed. And if we are lucky, we have a software update mechanism that can replace the whole thing. And that's maybe not where we will be in the long run. So when we talk about composable code, we are talking about putting code together from various sources, from various provenances. And we always have a trust issue. And one of the presentations has multi-tenant in the title, which is, I think, a very good comparison to something that happens in the physical world, where you have different parties in a building and they have to cooperate with each other, but we also have mechanisms that force this cooperation, like keys for those and things like that. So that's one thing that we will have to think about. More complicated thing is we don't just have to avoid any interaction, but we also have to do something like authorization or access control, because we may want to give pieces of code access to certain things that we don't want to give to other pieces of code, because we trust these pieces of code in a certain way to do something. So that's where an access control model comes in. I have to run these pieces of code in some level of isolation, and isolation right now often is a virtual machine or a container system. So that's also an interesting question. How do we do this on a device with very limited resources? We have been using the word mobile code before, which may be a little bit confusing for some people, because when they hear mobile code, they don't just think about pieces of code that are then composed together that come from different places, but they think about aspects like dynamic reconfiguration. So if you find out the peer you have been talking to has failed, you may need some additional code to actually cope with this situation. And you get that code maybe only at that moment. So things like that are thinkable. So the whole thing, of course, is a distributed system. It has always been a distributed system. It just gets some interesting aspects because on a single device, we actually have containers or virtual machines or whatever that essentially work together like a distributed system. So lots of questions. And of course, none of the things that are on this slide are in any way new. Of course, everybody is doing something like the things that are on the slide. The difference really is that we are now looking at the extreme left of the device cloud continuum. So of course, we know how to run containers in the cloud. We have ways to orchestrate them and to update the code in them and to stop and restart them and so on. It gets more interesting the further left we get, and it gets very interesting on the device. So the fact that some of these devices have constraints, of course, not all devices have particular constraints. If there is a Raspberry Pi or larger in there, then we can treat them like any other system in the cloud. But some of the devices have constraints. The temperature sensor doesn't want to use the power that a Raspberry Pi uses. And by the way, using that power would make the temperature reading bad. So the question is, can we do all of these things that we're already doing in a constrained environment? And of course, new questions come up with that as well. So we're looking forward to 3 talks that try to shed some light on these issues. So this is existing work. None of this has been in any way shaped by the research agenda of the Think Research Group. But of course, we expect to get input for that research agenda from these talks. So with that, I'll load the slides from Merlin. And hand over slide control to Merlin, and he should have slide control now.
All right. Thank you for that introduction. Let's see. Yes. So I am Merlin. I'm a researcher at IMEC, and I teach at Ghent University. And as part of my research and also as a hobby, I work a lot on open source and standardization. And so today specifically, I'll talk a little bit about my work with the W3C on WebAssembly system interfaces. So just to contextualize, like from IMEC's perspective, what the challenges that we are trying to solve. The average lifespan of a car in Europe is 18 years. So if you go back 18 years ago, this is what most developers booted up to. Beautiful Windows XP. Windows Vista was already out, but for some reason, not all developers liked it that much. And so the question is, how do you, this day and age, keep updating a device for which the software was initially compiled on a compiler for Windows XP? And the answer is, a lot of these companies either have Windows XP virtual machines running somewhere with those old compilers that they still use, or they basically look at software updates as if they are hardware updates and just tell users you have to install the new hardware in order to get any software update. And so software updates in that field happen incredibly slowly. It is not uncommon to find software packages which are security critical, like OpenSSL, that are over 10 years old in cars that are on the road today. This is an issue. In my opinion, WebAssembly is a great solution to this specific problem. Specifically, we can see WebAssembly as the glue between old and new. Instead of actually compiling your applications themselves with this Windows XP compiler, the only thing you have to still compile is the runtime. You can compile the runtime. It will have very slow updates, but that's not an issue because our applications themselves, we actually compile them with the latest tool chains, whatever programming languages you want, and you compile them into WebAssembly. And then you run those WebAssembly applications on top of that runtime, still compiled with that old compiler. And so the benefits of this is that you have a single WebAssembly binary for all devices. This can also help a lot with compliance, for example. You have forwards compatibility with new compilers and new programming languages over multiple decades. And each component is sandboxed on devices that are typically too small to even run a Linux kernel, let alone have containerization platform on them. This gives you language interoperability. You can compose components of multiple languages together, and it gives you an actual hardware abstraction layer, but not one that's custom to devices. Because if you look at the biggest users of this current WebAssembly hardware abstraction layer, these are cloud providers like Cloudflare, like Fastly. And they actually do a lot of the heavy lifting in order to get this hardware abstraction layer into libc, into compilers, and all that stuff. But very important, WebAssembly does this while still ensuring support for this pre-existing C or C++ code bases. Just recompile them into WebAssembly and it works. And it gives you almost near native efficiency in execution and compilation. So one of the examples that we built in order to show how this works is a Pac-Man game running inside of WebAssembly together with a USB driver running inside of WebAssembly that then communicates with a display and an external USB controller. And so both the application itself and the driver are running inside of WebAssembly. And so obviously, the first question is, what is the performance for this? And the answer is, well, it's actually pretty good. If you look to the middle, to class 15 devices, so Raspberry Pi, it just has an overhead of about 8%. And this is like 0.1 milliseconds or even less of an overhead compared to running this natively. This is very well. However, the overhead does increase when your device decreases. If we look at WebAssembly performance on servers in general, then it's basically near native. With the JIT compiler, we have like 1.15 times native performance, or with NeoT compiler, 1.02 times native performance. The interpreter is obviously takes a lot more overhead. But then if you go down to the level of microcontrollers, class 4 devices, then you are have an increasing overhead. For an AOT compiled WebAssembly binary, you can have an overhead of ×2. For an interpreter mode, you can have an overhead of ×40. However, if you compare this to things like MicroPython and Lua, then the overhead is clearly a lot less. These are obviously just like rules of thumb. Depending on your use case, the overhead can be higher or lower. The biggest downside of WebAssembly is that its memory overhead is always significant. I think one of the next speakers, I read his paper yesterday, and he actually has a lot better memory overhead, but still memory overhead, like I think it's at least ×2 for WebAssembly applications. Then before I go into this componentization, I just want to give a quick refresher for what is WebAssembly. WebAssembly is a compilation target. It is something you tell to your compiler to compile your application into. So you can compile your application into an x86 binary to run it on an x86 CPU. You can compile it to an ARM binary to run it on an ARM CPU, or compile it to a WebAssembly binary in order to run it on a WebAssembly CPU. But given that most CPUs don't actually implement WebAssembly, you mostly have to run it inside of a runtime. Although there is some interesting work building WebAssembly CPUs. The initial use cases for WebAssembly were simply the browser, because there is one big issue with WebAssembly originally, and that was basically the issue of how WebAssembly talks to the outside world. CPU-bound performance was near native on modern high-performance CPUs, but the moment it needs to do any I/O, the performance degrades a lot. And it is because WebAssembly, how it communicates with the outside world, is that basically your C++ application compiled to WebAssembly then calls JavaScript. This JavaScript code then calls the browser JavaScript APIs, and then that communicates with the operating system. So if you want to download a file, you go through JavaScript. If you want to access a USB device, you go to JavaScript. Even accessing the GPU, you go through JavaScript. This is obviously an issue. That's why the WebAssembly system interface was created. It's basically untangling JavaScript from WebAssembly since 2019. It is a WebAssembly native syscall interface, which is a standardized API to interact with host functionality and with host hardware, built for speed, security, and cross-platform support, and with the goal of completely removing JavaScript from WebAssembly. And so that's why you have WebAssembly runtimes now like Whammer that can scale down to maybe like 30 kilobytes in size, because they don't need to have a JavaScript engine anymore. Now with the second preview of WebAssembly, it included something very interesting for this research group, and it is basically a composition platform. Now, the WebAssembly system interface includes sandboxed polyglot componentized software with type-safe interfaces. It is being built by the W3C and the Bytecode Alliance, including many non-browser partners like Amazon, Cloudflare, Fastly, and Siemens, which are specifically looking at putting WebAssembly into microcontrollers, into actual products. There are already a bunch of products out in the field, millions of devices running WebAssembly on microcontrollers. So this is what creates this future of WebAssembly for IoT and edge computing. One of the things that we do with WebAssembly specifically is we are building and standardizing these interfaces for WebAssembly to communicate with the underlying hardware. The WebAssembly component model, as I said, this is part of WebAssembly system interface preview 2, componentized applications on top of WebAssembly. This is, in my opinion, a very, very interesting technology. It basically gives you typed interfaces between components, between what you would initially call WebAssembly modules, between the components individually, and also from a component to the runtime. It gives you support for any programming language with a component level sandbox. So basically linked libraries, but each library runs in its own security context and cannot simply access memory from other libraries. The way that I explain it is depending on, like, are you a developer or are you a sysadmin? Because from developer standpoint, WebAssembly components are basically something like Java classes, but you add isolation and you add support for any existing programming language, and then you get WASI components. Or if you come from the sysadmin side, it's basically you have a Kubernetes microservice application running on a device somewhere, but without the actual API overhead for these services communicating with each other. Instead of having to use HTTP, TCP/IP, or whatever to communicate, these communications between components are just simple function calls, sharing raw memory. What really makes this function is what we call WIT. It is a high-level interface description language, which allows you to build statically analyzable capability-safe interfaces. And this then has like translations into a whole bunch of languages with a standardized ABI, so that any language can talk this same language. And this allows you to do very cool stuff. So if you have a WebAssembly component and this speaks a certain protocol that the runtime does not actually understand, well, you can just add another component in that translates the API of the first component to an API that the runtime does support. So, for example, a lot of runtimes support simple TCP/IP sockets in order to communicate to the outside world. But a lot of components that are being built, specifically serverless components, they use an HTTP interface, which is a much higher level interface that allows to do a lot of cool things. Well, you can just add an adapter component in between them, slot them in as a WebAssembly application. And so now suddenly your host runtime supports additional functionality, supports additional interfaces or APIs. This also allows you to use WebAssembly as a universal plugin format. The common way to use WebAssembly for plugins is you have a host application that runs natively, and then this calls WebAssembly applications running inside of a WebAssembly sandbox inside of this host application. This is widely used currently in a lot of games, in a lot of proxies, in security policy agents, Shopify functions, and similar stuff. But we can also use this for device plugins. Componentize devices, componentize the software on these devices. They're basically, as I said before, well, we could actually just, the only thing that's running natively on the operating system is this WebAssembly runtime. And all the other components, including device drivers, applications, and everything, this can just run inside of WebAssembly. Moreover, because of how WebAssembly is built, all these WebAssembly runtimes, they are also purpose-built in order to be able to be included in an existing application as a library. And so even if you still want the performance of actual native code, or you need to do certain stuff that's not supported inside of WebAssembly, you can still actually do this as part of the application that then is the WebAssembly runtime. There is a big caveat, which is component model support. The WebAssembly component model is quite new, is quite controversial, and it is currently not supported in WAMR yet. WAMR is the runtime that I would recommend to any person wanting to run WebAssembly on embedded systems. However, this only supports WASI Preview 1, which does not yet have this component model. So even though you can slot in components and connect them to the host operating system, you cannot slot in components and connect them to each other. Only WASM time supports WASI Preview 2. So only WASMTime supports the WebAssembly component model. There's basically two solutions to this. Either WASMTime will shrink to the level of microcontrollers, which is work that Microsoft is currently doing in order to be able to run WASMTime on the hardware itself without an operating system, or WAMR might have support for a component model in the future. There's already some interesting proof of concepts showing how component model support could work inside of WAMR. So just to give you a little bit of an idea of what we are doing with WebAssembly specifically, I wanted to include a few examples. We are building the cyber-physical WebAssembly interfaces to connect WebAssembly applications to USB devices, I2C devices, and similar. We're also using WebAssembly for multi-party confidential computation. So basically isolating multiple different tenants in a confidential virtual machine so that they also can't see other entities that are in that same confidential virtual machine. We're also using WebAssembly in order to shrink the Kubernetes control plane because at the start of this talk, the previous presenter said that you can basically do anything on a Raspberry Pi, which is you can do anything except actually run a decent Kubernetes cluster, because the Kubernetes control plane can easily take up 1 GB of RAM just idling if you add some plugins. So we're looking at WebAssembly in order to reduce the footprint of the Kubernetes control plane. Then we have some research that is in early stages. Building a security policy framework for the WebAssembly component model, using WebAssembly to make it easier to run software in trusted execution environments for ARM Trust Zone and similar technologies, and building post-quantum cryptography solutions for WebAssembly. So I already talked about the cyber-physical interfaces. We do multi-party computation, where we basically combine data and algorithms from multiple parties into a single confidential virtual machine. And we use the WebAssembly sandbox to isolate tenants. We use WebAssembly to lower the control plane, basically by turning the Kubernetes control plane into serverless functions that only run that when there is a change to be processed, and when there's no changes to be processed, everything turns off. This makes a lot of sense unless you know a lot about Kubernetes, because this is not how Kubernetes works normally. And then a framework for building security policies for WebAssembly. And here, WebAssembly has an interesting functionality where they are so the WebAssembly system interface really tries to focus hard on capability-based security. So you give a workload a certain capability, and it requires a capability in order to be able to even execute the syscalls associated with that capability. Like if I never give it the capability to access a USB device, it doesn't even have a way to request access to that USB device. However, this has the problem that, first of all, it is not actually backwards compatible with how applications, how existing code bases expect to communicate with devices. And then secondly, with a capability-based security system, the granularity of your security functionality is inherently tied to your API. If you give it a certain capability, then all the functions that are part of that capability, if you strictly use capability-based security, all the functions that are part of that capability, it's basically a binary choice about whether or not you give that capability to a device. You can't then later say, oh, you have the capability to do this, but I still don't allow you to do this. This is why in our implementations, we actually add a second layer of security, a simple ACL-based security, where we have a lot more granularity. Even if a component has the access to request a certain syscall or request a certain operation, we can still deny it. And we're specifically working on better access control policy document format, which is standardized across all runtimes. Our hope is to get this standardized across all runtimes to describe the actual capabilities and then lower level access control permissions that a workload has. So in summary, in terms of performance, it's much faster than things like MicroPython, but you can still expect, especially on microcontrollers, you can still expect that it runs twice as long and that it uses about 5 times the memory that native code would use. Without you basically need to use the WebAssembly system interface for fast I/O. Without the WebAssembly system interface, I would not recommend trying to run this on microcontrollers, because then you need a JavaScript runtime on your microcontroller. If you need to run WebAssembly on tiny devices, go to WAMR. This will scale down up to a runtime size of 30 kilobytes. If you want to run WebAssembly on anything else, I recommend Wasmtime. It has great support for the component model. It has great performance, and it's actively being built by the people who are also standardizing WebAssembly. And in terms of security, WebAssembly with the component model gives you component level security boundaries with statically defined interfaces. This work is obviously not just my work. I have a very large team behind this, and the amount of names on this slide every year is growing longer and longer, so the font always has to change. All right, if there's any questions, I think we have some time for questions. If there's any questions, I'm happy to answer them. So the question is C4 and C15 referring to the RFC classes from IETF? Yes, those are the classes that I'm referring to.
Yeah, so we indeed have some time, I think 8 minutes on the agenda for the questions. So please think about your questions. You can say them as I'm doing right now, or you can actually put them into the chat, as I already did, for example. I have a question that maybe doesn't have a simple answer. So much of the WebAssembly work was based on browsers initially, and the systems that are class 15 or more. One question, of course, always is, do we have an impedance mismatch? Does something no longer really work? And it was, for instance, interesting to see your ECL example. In the end, on a microcontroller, this probably needs to be some binary data structure that's somehow configured. So what processing steps, like looking at these interfaces in interface description language and so on, needs support from outside the constraint device so you actually can run things? And of course, the next question will be, do you have a plan how to manage the trust relationships to actually make this happen? But that's maybe beyond what we can do today. So my question is, can you do all this on a constraint device, or do you have to outsource something to other components?
Okay, so your first question, if I understand it correctly, is about kind of microcontroller-specific WebAssembly changes that need wider support. Is that what you're asking?
Well, you can build a system in such a way that you just assume you have lots of support functionality, compilers that run in the background and do just-in-time compilation, and so on. And if the more things you add to this, like an interface description language and so on, the more complex this support becomes. And maybe another way to ask this question is there a place where you actually can place a boundary between stuff that actually runs on the microcontroller and stuff that runs elsewhere, and where the microcontroller simply needs to trust that elsewhere to produce results? So if you do ahead of time compilation, for instance, you have to trust the place where the ahead of time compilation runs.
Yeah. That's also why I included the numbers for the interpreted WebAssembly, their performance, because that's like the case in which basically everything happens on the device itself. You give it a WebAssembly module and it runs there, and there's not even a compiler or anything that you need to trust. Whereas with ahead of time, obviously you need to trust the device where the WebAssembly binary is converted into an ahead of time binary. When it's about these with interfaces, this is actually a step that is most relevant before actually creating the WebAssembly binary. There are generators in order to turn these with interfaces into language-specific, I would say, skeleton code that then does the lifting and lowering from a common ABI into what the application itself uses and what the programming language uses. And the only thing that's left in a component is just an optimized version of the description of the interfaces itself. And so the only thing the runtime needs to support in order to support these components is understanding this description language and being able to connect it to other devices. But then based on these descriptions, the runtime will set up the security boundaries. And so in that sense, there's not really an external place that you need to trust to set up these security boundaries. These will be set up inside of the runtime.
Okay, Emmanuel has a question. Did you want to say that, Emmanuel, or should I read this out?
Feel free to read it out. I mean, I was just wondering if you said there was some ongoing work with Wasn't Time, and I was wondering if you had like any more details on that. We have some ongoing work on Wasn't Time too in Ariel West, and so I was just wondering like, if you had pointers or news or whatnot. Would be nice to have like a single runtime to focus on. We also work with Plumber, as you will see in the next talk.
So the work that I was specifically talking about, I do not know of work specifically to run Wasm Time on microcontrollers, but I do know of work that Microsoft is doing in order to run Wasm Time basically without an operating system inside of a virtual machine. And that is basically the first step in order to be able to run it on microcontrollers. This is a PR on the Wasm Time repo, or it's already merged, I'm not sure, but it's part of the Hyperlight project of Microsoft.
Thanks.
Thank you. Kerry, do you want to say your thing?
Hi, Merlin. I'm basically new to this work, and I'm just wondering about the inter-component communication model and whether any sort of concurrency primitives might be necessary to sort of coordinate information flowing between the different components.
Yeah. So I think there maybe the first thing I want to say is there's a big difference between whether or not you have an application that has a runtime embedded in it versus whether all your application components are running inside of the runtime. If you have an application with a runtime embedded in it, then you can implement any concurrency methodology that you want to use. You just implement it inside of the application itself. And then instead of spawning threads that communicate over, for example, channels, then you just spawn WebAssembly threads that communicate with each other over channels. In such a framework, WebAssembly is just a function that you run. However, if all the components run inside of a WebAssembly runtime and you want to have concurrency in there, then what is currently supported within WASI is basically poll-based asynchronous communication. One component does a request to either another component or the runtime, and then just keeps polling to figure out whether or not something has changed. But they are actually for, I think it will be in WASI Preview 3, there will be a fully fledged async model inside of WASI, which from my perspective, I'm not an expert on async work, but from my perspective, any concurrency framework for any programming language should be able to be implemented using the concurrency functionality of WASI Preview 3. So that's something that we're specifically looking forward to in order to bring concurrency in a much better way into our USB standards, for example.
Okay. Thank you. So we have used the allotted time. Of course, we can bring up more questions if they occur to you in the discussion segment later on. But for now, thank you, Merlin. And the next talk, I'm going to try to bring up the slides for that. Interface is a little bit arcane. Okay, so you should have slide control, Carolina.
Thank you. Hopefully you can hear me well.
Yes.
Awesome. So hello, I'm Carolina Skrivankova. I'm currently doing a PhD at University College London under Mark Handley and Steve Hales. And my talk may have a very unwieldy name, but essentially what I would like to do is, first of all, give some context about what I talked about in Madrid in the last meeting. Then talk a bit more about what might be the end goal we're building towards, which is to get stable and reliable control applications over IoT infrastructure, which are distributed, and what we're doing in our work to support that using managed communication channels and system signaling. So there is an issue with industrial automation industry. So we have a lot of equipment with very high costs. It's an ecosystem that is highly ossified. There's a lot of vendor lockdown. And well, we really would like to use automation so that as the systems we control go up in scale, we decrease the costs and resource usage, and we improve user comfort. But this is not what really happens in reality. As we increase scale, usually we see increase in costs and decreases in reliability. And in automation systems, so things like building automation in commercial buildings, or it could be something in utilities, we want systems that can evolve over decades because that is the expected deployment time for these kinds of systems. We want to be able to gradually change how they're used and also gradually be able to change the infrastructure underlying. We want it to be resilient to failure and, of course, secure. And there's a lot of headlines recently about various attacks on many types of critical infrastructure. So it's quite a hot issue. So what is that we're doing, and what I talked about last time, is that the idea is, could we actually get reliable and stable distributed control applications running over IoT infrastructure, in particular over microcontrollers such as ESP32, because they have come to a place where the microcontrollers are very cheap, but they're fairly, they have a fair amount of resources available to them. So like an ESP32 has maybe half a megabyte of RAM. And what can we do to bring them to reality? So on the left, like we have a fairly simple example application where we're collecting some, we have a control policy which has kind of contains all of the computation control logic that we want to execute on our system. And what we do is like divide it all up into containers, which we then distribute over our microcontrollers. So like on the left, we have containers with various roles. So for example, some that collect data, then send it over to container that does some processing of the data. For example, fuses it by calculating an average. Then moving on to making a decision on whether to turn an actuator on and off, which then sends the actual command to a final container, which actually actuates on the actuator. So we would like to be able to adapt the system over long periods of time. For example, moving to the right, if we're adding a new device, first of all, we might want to make use of the better performance of that new device. And so we want to move and offload some of the computation to this new device. And also we need to be able to integrate new sources of data. Then also going back, if that new device fails, we still have all of the resources we have in order to restore functionality. So you want to make sure that we do restore that functionality. That is not always possible. For example, if we lost the link between these two devices, we don't have any sensors that could actually help us to do useful inference. But maybe we can reach a different device which has like some other type of data, which is not as good for the inference we're trying to do, but it's something, and the system still works until we get to it and try to fix it. And then, of course, we would like to add new services with our existing infrastructure. For example, using the data we have, like from our sensors, to input it into an anomaly detection module and report it to an external server. So what we're trying to do is get decentralized and local control in independent involving components or containers. We're trying to limit fate sharing between components by the way we use communication channels, which we'll talk about later on as well. And the main one of the big points here is we're trying to design interfaces for resource access that enforce certain guarantees a control application developer may rely on. So what are the target domains that we're talking about? It can be something like a commercial building, a whole university campus, scaling up even further city infrastructure, which have particular property that they're not really automation, which is central to someone's business plan. It's not a thing that makes you money. It needs to be in the background, save money, and we want to interact with it as little as possible. But it also applies to domains such as utilities, water companies, grids, etc. All of these have a lot of complex stakeholder involvement and ownership, with involvement with private companies, public institutions, lots of legal constraints and organizational complexities. They're usually large in scale, often both geographically and in the number of devices. And the expectations for these types of systems is that they're going to be deployed for decades, long periods of time. They also have, what's different between them is usually how sensitive they are to latency and what are their real-time requirements. For example, a building automation might work on in a range of deadlines of like hundreds of milliseconds. So let's just go through an example of a very fictional university called WCL, which manages a portfolio of about 300 buildings with limited budget because the international students are not there to fund the university in place of the government. So it's a combination of some leased, some owned buildings. In some cases, it's just a single floor inside the building, and they've been acquired at various points in time. Now, what we use to automate things like ventilation, heating, emergency systems, etc., in these buildings are from vendors like Schneider, Honeywell, and we're buying lots of very expensive controllers, like the one you can see on the lower left. One of these can set you back by like £2,000 to £4,000, mostly because we have some reliability guarantees about what the hardware can withstand and having lots of I/O. And alongside it, we're also buying into a proprietary platform, which actually allows us to do anything useful with it. So apply our control policy and like use the devices and actuators and sensors that we deploy in our buildings. So because the engineers in managing these estates have to work with acquisition teams, often their requirements aren't fulfilled and they don't get solutions that they would like to use because they're too expensive. Also, switching between any of these proprietary solutions is incredibly expensive because usually we would have to switch out all of the controllers, we would have to train new people, etc. And so as a result, what happens in a single building, even a single floor, we're often running multiple parallel control systems. There is no global view of state. It's very difficult to apply any kind of uniform policy, for example, in terms of energy efficiency or even viewing how our buildings perform is quite difficult. Now, this also means that any fixes and updates take a very long time, require a lot of manual intervention, and so they often aren't done at all. And because the teams are often very time and money constrained. What happens on a single device that actually executes our control policy? So first of all, any compute that we run on the devices needs long-term support because the system is going to deploy for long periods of time, or we need to have some ability to switch between vendors. This would also bring some better incentives into the ecosystem because if it's very difficult for us to switch, the vendor likely doesn't have many incentives into investing into giving us better solutions. This also means that we would need some well-standardized interfaces to communicate between different parts of between our different control tasks in order to support functional service, so interoperability. If we containerize our control tasks and we want to deploy them in our system, there are some constraints that some of them might be under. For example, they might need certain memory or processing limitations, or they might need access to specific hardware peripherals like sensors or actuators. They might also be under various timing constraints where they need to get or send data under specific deadlines. So in order to successfully support execution of such a distributed application, we need to provide some service guarantees for the containers. This is especially true if we're hosting multiple containers with different roles on a device, since we have to handle resource sharing and maintain the guarantees required for all containers which are hosted. So in our work, we've been using WebAssembly to support our independent chunks of control compute. And it's very lovely because it provides us things like component isolation. There are some security guarantees, but these are, as Marilyn also noted, these are often related to the runtime. We're using WAMR, which requires some extra verification for security guarantees. It also provides us with portability, which is lovely because we can the implementation of a control application that doesn't need dependencies on a specific hardware platform. There have been historically some concerns about the domain crossing overhead, but as Marilyn also noted, this doesn't have to be the case, and the performance tends to be quite good. There's also very good developer support, and interestingly, in theory, there is no reason why we need access to WebAssembly source. So it might give us a way to support something like a DRM to just improve any market incentives for participants. Because if we want people to, of course, invest into development of software for these kinds of large, complicated systems, we need to be able to protect their IP. But there are also some unresolved issues. First of all, if you were talking about microcontrollers, so things like ESP32, there are some design decisions in widely available runtimes, like production-ready runtimes like WAMR, which is that the way they handle resources isn't ideal and is still fairly heavy for a microcontroller. There is a lacking support for interfaces, which there are some efforts in WASI, as again, Marilyn mentioned, but these aren't usually with consideration for something like a control application. Then if we need to be adhering to timing constraints, we might be asking about what is the execution scheduling model for the containers on our device, and what is the related latency to interfaces, especially if we're communicating over a network. And of course, if we're talking about deploying these kinds of systems for critical applications, well, even if they're not critical, even if it is something like building automation, we want to make sure that we check the provenance of the containers and possibly even verify that the container does what we think it's supposed to do in order to support open ecosystems which are secure. So our work, or the result of our work, is called Chaos, which is something like an operating system based on FreeRTOS, which runs on the microcontroller and provides lifetime container management for WebAssembly to make sure that the compute is kept alive and reachable somewhere. So every time a container arrives on the device, it comes with a signed manifest with a list of permitted capabilities. And it also handles access to the outside world, so which includes things like HAL, although that's a domain that has been discussed in Marilyn's work, and I'm not going to talk about much, but I will talk about inter-control task communication, especially when this happens over networks. So for example, between this read and average task on the device, and system event signaling. So for our inter-task communication, instead of going with something like an RPC, we decided to implement communication channels, which define two endpoints, like using between two containers using message passing, which gives us a fairly simple interface of get and put with checks and verification on types of data. So there are different states that the message channel, communication channel can be in, including running, paused, or failed, in order to synchronize how data is handled, especially during something like migration or failure, which can be mostly detected inside an application. So the communication channels are mostly hosted by the OS, not the container. This helps us in cases like, for example, when a container fails, the data that it's submitted is still existing within the OS. Or if we want to migrate a container, we can start the compute somewhere else while having retained the data which has not been processed before and just redirect it to a new place. This helps us with limiting fate sharing between containers and try to prevent spread of failure. So one of the questions here is, how do we find a container? How do we specify its identity? Because it's not enough to identify it by the device where it's at, because its location may change if the system conditions change. I mean, we want to reconfigure our deployment to fit a new set of requirements. So what we came up with is something like a semantic address, a tuple of a service ID, which is a bit of an abstract concept I'm not going to go much into today, but this describes like possible various services running on the system, which might help us to handle resource sharing and also semantic information about the data flows in our system. So for example, in the application we had before, we have two services. So one of them flows from the collecting data from the sensor, we're calculating an average, and then either we provide the data as a source of inference for an actuator, or we plug it into an animal detection model. Now, this gives us the ability to look for containers or address containers, but to get addressing which is per container, not per device. And also, in theory, to handle shared resources. For example, if a container is talking to a sensor that multiple services need, then either we would have to handle that and handle it very carefully within the OS, or we can push that complexity into a container and give the container a set of identities that different services can access. This, of course, needs a very good mapping service to have knowledge of where any container is at a given time if we have to talk to it. So we decided to not provide direct network primitive access to our control tasks. So they're not allowed to open sockets. They always talk over an interface to communication channel, so message passing channel. And well, one of the reasons for this is thinking, if a malicious container containing malicious code happens to be loaded on our device with that signed manifest of capabilities, what could it do? And this partially helps us to restrict the capabilities of a potential attacker, because while it can still forge data, so for example, it can still forge sensor readings, it is restricted to certain setting schedules, setting semantics, and at most that it can overwhelm is a local message queue in the OS. Again, this allows us to loosen the coupling between the different components because it's hosted within the OS. So now this brings us to a question of, well, if we're exposing the network as a set of services, what set of services should these be? And we're thinking about this in terms of, well, what are the types of data that we might like to transfer between containers in a control application? So this can be something like fresh sensor data, where we don't really care much about reliability. We just want to get the freshest data possible. If it's been 5 minutes since data point was generated, we don't care about it anymore. or it can be something like command and event updates, where losing a single command might change the correctness of a computation. Of course, there are also different latency constraints, which are partially control domain specific. And so there are two big segments to this. One being what are the reliability modes we would like for different types of data. So for example, fresh sensor data versus commands, where CoAP is actually provides a very good service for datagram delivery. And there's also the question of data transfer initiation. Who initiates the transfer of data? Is it the sender or the receiver? So mostly when talking about IoT, there's a lot of pull between different pieces of compute. So where there's a request and response, which is great, especially if we have nodes which are only awake intermittently, but doesn't really fit communication channels where periodic delivery is expected. So for example, if I'm sending a sensor reading every 5 seconds, being able to pull the data to my next neighbor might be a lot more useful. So then we would also, we give the container the ability to have some restricted access to various resources in the outside world, but we might also like to notify it about important information that might affect its lifetime management. So first, it could be just the state of the communication channels it has, so its inputs and outputs that talk to its next neighbor. So for example, we might, like in this example, we might be able to accept a new source of data. So for example, here, the calculate average task on the right would like to accept a new source from the new sensor. But also we might lose communication channels as things fail, and we need to reconfigure things. This is also where having communication channel states come into play, where if a communication channel is failed because of a detected link loss or loss of data, the application or the OS can know and communicate this information. Because part of what we're trying to do is support changes in the deployment, and so support container migration. If the computation we are doing is stateful, we might need, and we want to move a container, we might need to do a state handover. So that is one where a container gets a notification that it's going to be terminated within a certain period of time, and it has the time to finish any computation test and hand over state. If it cannot do that, it will be reset. Now, a reset is especially useful if we have chains of application containers with some stateful computation. For example, if we're sending data differences downstream. So if this middle container sending some data differences downstream fails, we need to alert the downstream application containers that this has happened and the state they will be receiving onwards is not has changed, and they have to restart their computation as well. Which helps us to deal with chains of control applications which are stateful. So this has been a lot of topics, but in summary, when building control applications from containers, one of the really useful things it gives us is the ability to limit fate sharing between components, which it also extends to the interfaces we use between the containers. We would like the interfaces to be fairly simple and feature-proof, because these are the things that stay. While we're able to change the containers, we're able to change the runtime, we have to think very carefully about how containers access data in the outside world. and how they interact with the underlying operating system to get information about the state of the world outside if it needs it. So the interfaces need to support, they need to be secure and support certain guarantees that a developer can rely on when thinking about deploying these applications on the system. And we need to be able to figure out how to handle shared access to resources and meeting time constraints for the control applications we're targeting. Thank you.
Thank you, Carolina. We are almost at the end of this slot, but I think we can make some time for questions because we already had a little bit of the discussion that we are scheduled to have. So if you have questions, please raise your hand or type them into the chat or just start speaking. So one question that came up in my mind, you have talked about security. You haven't used a term that people who sell these $4,000 controllers usually have in mind, which is safety. So do you have any idea how your architecture would match up with safety requirements?
So safety requirements meaning safety of the control that you, so like stability or?
Well,
yeah,
I have
I know
building and there is a heating device in there, and there is a certain tendency not to want this heating device to overheat.
Yeah, so like control stability, right?
Yeah, I mean, generally there are things that safety critical people want certified and don't want to touch and so on, and you have to somehow interact with them or implement them in a way that they can certify it.
Yes, so you need to, yeah, that's definitely consideration. So like part of that would be if you're executing, so like if you do have an open ecosystem, like where different vendors can provide you with like pieces or like with services for a control application, you need to be able to, like, I suppose, verify that does what it needs to do, and the software needs to be like follow certain constraints to be safe to deploy. So but it's mostly an application. Okay, it's largely an application consideration, but of course, if your system cannot meet the latency guarantees, that would be an issue, and you need like a safety state. I forget what this is called in English.
Okay, yeah, that was a really difficult question. So I wasn't expecting that you have a complete answer to it. But it would be interesting to see how safety considerations actually influence an architecture like this. So maybe that's just a research question that I'm raising. So Emmanuel is in the queue twice and Carrie is once. Maybe Carrie can start.
Oh, so, hi, great talk. I'm just wondering if you've given thought to data models at the application level and whether you're trying to remain agnostic, at that level as well, which is which presents its own problems. How do you translate between various application data models?
So yes, so we're exactly trying to remain data model agnostic, and we think that the data model should be handled on the application level. What we're trying to do is to provide you with like reliable infrastructure for you to deploy your application on. Like there are like many different approaches that I think that handling data models on network level is generally not a good idea because it really it implements a lot of constraints into your system. So we are trying to remain data model agnostic.
Okay. Emmanuel?
Yeah, thank you for this talk and for describing this use case from this anonymous university. And yeah, so the question written in the chat is pretty much self-explanatory. Like, so if people were to try to use what you implemented or designed on another OS, because people tend to use different types of OSs, like how much work would that be?
So the biggest thing you would need to re-implement is mostly, the biggest dependency is the runtime, and also the execution primitives. So we're building on top of RTOS, which means that everything is scheduled within threads in a task. So it's tied to that. So mostly you would, Warmer, I think supports Zephyr and possibly Ride. I'm not sure about that. I don't think it does. And we are relying on some WAMR semantics, especially for imports and exports. So I think that's about it. So you have you have the runtime semantics and scheduling primitives that are mostly different. That's it shouldn't be too much work. One that we potentially, if I have enough time in my PhD, I would like to actually implement the system on a different platform, but I'm not sure I'm going to get there.
Yeah, I think that was a pretty good question, because if we are trying to do research, we have all these components that run on different platforms, and we never managed to actually put systems together that actually work, because everything is designed for something else, and we need to get in a situation where we actually can quickly build systems, and I'll come to that later. So Crystal asks whether the work is available.
Yeah, so also to that, it was definitely a consideration for us to try to make sure that it's portable, but whether it's available, okay, so I've been trying to get it available for a long time. Now we're preparing for publication in November, so by end of November it should be out and open source.
Great. Okay, any more questions? Okay, so in that case, thank you, Carolina.
Thank you, everyone.
I try to switch to Bastien. Well, that was not the right button. Sorry. Okay, now you should have slide controller.
Okay, so hello everybody, I'm Bastien. I'm a PhD student from France with Orange and Lucknow, and I will present you my work on a multi-tenant microcontroller using WebAssembly-based containerization with the use case of putting TinyML as a service on the multi-tenant microcontroller. So first, when I'm talking about a microcontroller, I'm talking about class 3 microcontroller with some 200 kilobytes of RAM and reduced processing power. On this microcontroller, we use some lightweight containerization. Today, we'll present you some work using WAMR, but there are other work like RBPF. Also, to manage this container remotely, there are multiple platforms. At Orange, we develop a tiny container, but other platforms like T2TRG propose an equivalent of a container management remotely, or there is also a micro-RG. The containerization allows to have a multi-tenant microcontroller, which are devices on which multiple applications from multiple actors are deployed. And you can see on the right a typical multi-tenant microcontroller with a container, a runtime, a management agent to manage the container, and the OS and the microcontrollers. So the multi-tenant microcontroller allow new kind of services for the microcontroller. It's a servitization. It consists to allow third party to develop services for your microcontrollers, and it allow things like App Store. Why it is a good thing? Because it's allow to customize the user experience while allowing to monetize the device for the person proposing the device. And we want to do servitization with one type of service, which is TinyML. So TinyML, it consists of running machine learning model on a constrained device. And today we'll concentrate on doing inference. So it consists of doing prediction with the model, and I will not talk about training on the microcontrollers. Running inference on microcontrollers allow to have privacy because you are processing the data on device and also filtering the data if you want to have a first layer of processing before sending to cloud. So we look at what work there were on doing tiny machine learning as a service, and Doyo et al. Propose an architecture to deploy TinyML as a service on microcontrollers. It's simple. The device requests some TinyML, and a cloud platform will recuperate a model, process the model to produce some code executable on the device, and deploy the code on the device. The issue is that you are putting third-party code on your device, and you don't know what the content of the code that you put on your device. So our proposition is to use WebAssembly to put the code in containerization and to safely run the TinyML code. So first, I will present you the architecture that we have proposed to do TinyML as a service with WASM containerization. And then I will show you CS4Warmer. It's a framework to use the WebAssembly runtime, the micro runtime, and to counter some limitations that we have found while using Warmer. And all of our work are available on GitHub. So first, the architecture. To design the architecture, we have a look at the different needs of TinyML. We first the need of computation optimization, as TinyML is very resource intensive. We need some guarantee on available memory because TinyML consumes a lot of RAM. We need isolation to protect both other applications on the device that don't want to be interfered by the TinyML model, and to protect the TinyML model because the weight of the model are business value for the people distributing the model. And finally, we want some fault tolerance to allow to have, even in case of issue, to have the possibility to restart the container and restart all the application in a working state. So our architecture to deploy TinyML as a service on the multi-tenant microcontroller work like this. You have in blue on the right a service container that will request the TinyML service. Then the cloud platform will recuperate a model and a compiler to produce some WebAssembly code. So instead of directly producing machine code, we produce a WebAssembly code. Then we can give it to a trusted container management platform that can do some optimization and do some ahead-of-time compilation. And then the platform can deploy the TinyML model so it can be used by the service container. So we implemented the generation of container and the execution on a microcontroller. We use a RiotOS and a Whammer. And we have chosen a model that fit on the microcontroller. And it was a real challenge because a lot of the model are very big. And with the RAM overhead of WebAssembly, we were often hitting the limit of the microcontroller. What we have seen when implementing the different container is that the first challenge we have, it was that how to call the container from other containers. One thing would be to use a component model that you have seen in the previous presentation, but the component model is not available on Whammer. So we try to look how to do it. We could possibly link directly the different service and sharing the memory, but in this case, if we share the memory of the container, it will let the other container, for example, the service container, to have the possibility to have access to the memory of the TinyML container. So it would not be a good thing. So what we have done, we have implemented a native function. It's more or less like a WASM driver that you have seen in the previous presentation to interact with other modules on the device. When running the TinyML model, we have seen that the interpreter and interpreting directly the WASM file on the device was not possible. We had multiplication of the execution time by 96. But when doing ahead-of-time compilation on the cloud and deploying the compiled code on the device, we have seen performance equivalent to native execution. In terms of RAM consumption, we have tried to reduce it as much as possible by using end-of-time compilation and execute in place. So execute in place consists of allowing the runtime to execute the produced code without any copy or the less copy as possible to reduce the RAM consumption. But it can be difficult to set up to have a IoT code that respect execute in place. So we have an architecture that allow us to deploy TinyML model as a service using IoT. We still have a high memory overhead, and for TinyML, we have also seen other challenge, like the lack of connection with underlying hardware. And for example, on some device, there was a AI chip that can possibly be used, and with our proposition, it's not possible. Maybe with some WASI API, it could be a possibility to access the underlying hardware. So when we have implemented the proposition, we have seen some limitation in Whammer to have a full control on the memory usage of the module, on the permission that we can put between the different modules. If we can define a native function, but they are global for the runtime, the memory used by the different modules are not separated, so it's difficult to implement hardware isolation, and we didn't have some restoration mechanism. But the three things that we have first presented, they are all available in WAMR, but configurable instance-wide. So what we have proposed is to use one instance of WAMR per module, to use instance-wide configuration of WAMR to have a lot of a more precise configuration for each container. So how it works? It works only on a single core device, and it switches the currently used instance of WAMR while using the different module. Some limitations are that the override are dependent on the use scheduler of the OS, and we have no built-in intercontainer communication, and we cannot use the one of WAMR because we have no separate instance of WAMR. So to conclude this presentation, we have a TinyML model running on the microcontroller using WebAssembly. We have good permission, granular permission, and we can pen some memory control on the usage. But we have high consumption of memory, no underlying access to the, we have no access to the underlying hardware. We need to implement our inter-container communication code, and we have not yet hardware isolation of memory. So thank you for listening. I will be pleased to respond to your questions.
Thank you, Bastien. Thank you for almost keeping in time. This was a tall order to do this in 10 minutes, and you did it in 15, so that's great. Thank you. So are there any questions? Oh, there's one. Merlin, go ahead.
Yeah, I wonder what the difference is between this and if a WAMR runtime in the future that would implement the component model. Is that the kind of security that you are looking for?
Yes. There are multiple things. Some WAMR are allowed to have some control. For example, I think on the WASI access on the WASI API. But here we are not using some WASI, so system interface of WAMR. And when using system interface of WAMR, we have a very few control on the different permission of the module. So maybe if WAMR, yes, maybe if WAMR implement a component model, they will also implement a fine-grained permissions that will allow to have a similar consequence as our proposition.
Yeah, I think maybe is a third problem is that currently within the component model, I don't think it is possible to have multiple components that have different permissions on the same interface. So
yes.
that's also something that would need to be solved in order to be able to do this with just the component model.
Yes.
More questions? Okay, so thank you, Bastien. All the slides are available on the site that you can find if you go to the chat. The chat is accessible from the top menu with the two, what do you call this? Sprechblasen. What's the English word for that? So there is one more question? No. Okay. Emmanuel.
Yeah, just maybe one question to the chairs, like what kind of like next steps do you see with this, you know, line of works and type of issues that we just discussed now?
Yeah, that's of course the assignment for the whole group to find out the answer to the question. So I actually have a couple of slides I prepared during the meeting. Let's see if I manage to start them. Okay, so that was the text that you should have read what this meeting is about. This already asks a lot of questions, but I try to list the questions that actually kind of impressed me the most. And obviously, the one thing that we need to understand to make this work in the long run is what is actually the set of stable interfaces that we are using, and how does the architecture look like that puts these interfaces in place and allows the evolution. And apparently, the architecture work has a lot to do with the distributed aspect, which I think is quite interesting, because we occasionally heard the word CoAP, but there are also other modes of communication that we want to put in here, and that also comes in when we talk about the interfaces. So one thing is the on-device hardware or bus interfaces, and how do you actually do the granularity that you need to actually support a multi-tenant situation. And the other question is, how does the communication interface look like? Of course, being an internet research task force, we are thinking in terms of internet communications, but the abstractions we actually provide in the interfaces to the various components may need to be different. And for instance, they may want to make the communication between containers on that one device and between containers in the distributed system similar enough. They cannot be the same, but similar enough that you actually can switch between them without breaking things. And we also, of course, need communication interfaces to whatever is out there, BACnet and KNX and whatever Modbus you have there, and how do these communication interfaces look like? Do they have any commonality with the communication interface we use between containers? So that's an interesting question. But behind these questions are probably a few things that I just called operational considerations. And I think that's a set of questions that will come up, and that we essentially can make part of a benchmark, of a standard set of evaluating some proposal. So one thing that we noticed is that there is a certain expectation that there will be a difference in the velocity of software updates. So one assumption might be the base software that runs on the device is updated much more slowly than the individual containers that run on top of that. But that, of course, means you don't want the components that tend to break all the time and need to be updated in the base system. And communication software, of course, is the most vulnerable part of most systems. So that's interesting. I quickly mentioned safety critical versus security critical components. That's another benchmark question. How can you accommodate safety critical components? I think we briefly discussed trust issues with offboarding. I think things always will have to benefit from more powerful friends in the network. The question is, how do you actually evaluate that friend status and so on? How do you actually do dynamic reconfiguration? So who is the node that actually has the information to actually do that? We had an interesting mention of identity issues. So if you have all this software being instantiated tons of times, how do you actually talk to the individual instances that come up? And with addressing, of course, always comes routing, or at least finding the other instance that you want to talk to. And that immediately leads to the next question: how much of the existing infrastructure can you actually use? So those Ethernet switches that are in the rack, are they useful for this application, or do we need something completely new, like an ICN model of networking, just this time maybe about control operations? So I think these are a few questions that we can all keep in mind when looking at various proposals in the space. And I was hoping that we might collect more of these kinds of questions. And of course, a lot of questions have already been raised by the talks that we heard today that I didn't put on this slide. I tried to put things on this slide that maybe weren't explicitly mentioned. So how do we work on this? And I think mostly the products, well, maybe at some point we will have RFCs, but mostly the products now will be proofs of concepts that other people also can use, work environments, benchmarks, challenges. And what I would really like to see is that people who have a certain system concept in mind offer something like a starter set, which is configuration, connecting the right pieces of software together, maybe with a board recommendation, buy this board, and then you can run this without fighting with board control modules or whatever, and making choices that of course can be changed, but you can get stuff running quickly and run experiments on them without necessarily being the original author of the software. So that might be one result we could work on pretty quickly. So we get to play with each other's toys and make interesting observations about them. Then maybe we want to define benchmarks from things like the benchmark questions on the previous slide, and maybe even challenges. Can you do that? And I don't have an answer what that would be at the moment, but I could imagine that when we think about that, we find answers. And of course, we need to find the events where we actually do this. These events can be online, they can be hybrid. For instance, the hackathon that will happen on November 1st too, that is hybrid, and we usually get some interesting results at hackathon. So that may be too early, but maybe it's worth thinking about what we can do today. So does that answer your question?
Basically, it does.
Good.
Thanks.
So we now just have to start doing that. And yeah, we had a slide on the chair slides that talked about, oops, that was wrong. Talk about, where was it? Yeah, upcoming activities. So the next thing that we are all looking forward to is the IETF 124 in Montreal. That of course is pretty close to now. That's in 2 weeks. So we won't be able to prepare a lot here, but we might actually do some of this work at the hackathon. That's on the weekend before the IETF, November 1 and 2, and it's a hybrid thing, and it's free of charge, which is good. And also in particular for the people who are there physically in Montreal, we will try to get together on Monday morning at 8 a.m. We have a room reserved for that, and that's a so-called side meeting. And well, this is mainly useful for informal communication. So we won't have the projector showing slides all the time, where maybe a couple of slides from some people, but we also want to make sure we actually talk to each other. So that will be an opportunity to go beyond what we have done today, and of course also with other topics that we have been working. And then the most easy tool we have is doing interim meetings like the one today. And we might do one more this year after IETF 124. That might be about AI agent topics, which are also very interesting at this point in time, and of course get a lot of attention. Or if we think we actually have something that we could do in this phase, we could do even that. So that's what the mailing list is for, to discuss this. Okay, so this is supposed to be a discussion slot. So I said too much, but maybe you have observations about my observations, or have your own observations that you would like to bring up, Carrie?
I actually had a question for Carolina if she's still on, but I couldn't reach the mute button fast enough. But Carsten, one topic I know that was, sort of a core thing many years ago was pub/sub. And so my question for Carolina is, to what extent do you think that pub/sub could be an important, like, intermediate technology between various components that want to communicate with each other, or perhaps even, look back in time for, near resets, that sort of thing?
Yeah, I think it's one thing with pub/sub, so like things like MQTT, at least that I'm familiar with. Like the issue is that they require you to have some kind of central broker, which does kind of violate the goal of having like local decentralized compute. So I presume like there are some like protocols which do not have that consideration, but I think that has been the biggest constraint to that. And also, I suppose you have to start thinking about like the semantics of how do you, like, what does it mean to request a topic? Like where is, you have to be pushing again the data model lower down below the application if you want to handle that in network. If that's answers anything.
Yeah, Carsten, this may relate to your question of, what existing infrastructure can we use to sort of advance, solutions in this area? I don't know what your thoughts are about it, but.
Yeah, so we have been focusing on certain communication primitives for a while, and CoAP is the expression for that. But then we also have documents like the one I'm just mentioning in the chat, which is CoAP pub/sub, which is looking at a communication situation where you can use brokers, but you don't have to use brokers. This is based on CoAP, so maybe that's overhead for you, however you look at this. What I also could mention is that there is some work in the ANIMA working group of the IETF that is looking at the GRASP protocol. The GRASP protocol was originally designed to do network management in a situation where very little of the network management actually works. So it has a very simple communication model. And there's currently work underway to do a constrained grasp, which works on a small node that cannot keep tons of TCP connections to its peers open. So I think this revisiting of communication primitives is really quite active subject, so constraint grasp may change the reliability model of CoAP at some point in time, or add to it at least. that may be a spin-off activity that could be quite interesting for the research group. Now, of course, there are millions of different models how to do communication, how to structure it, and the message queue model that Carolina managed, of course, is a component, but it's usually just a layer in something that has higher layer components. And finding out things like PubSub, which is a certain way of handling the data, is really interesting. And then we can send off the IETF to actually do the protocols for that, or actually they are doing this in the case of CoAP PubSub. So if we have, that might be something that can be put on a separate slide here. If we have specific ideas of communication primitives that are different from the classic client-server situation, the REST situation that we are addressing with CoAP, and the message broker situation that MQTT addresses, it might be useful to actually write them up and even maybe guide them to a prototype implementation.
What I also really like about the slides, and also what you touched upon already, is that it starts to, I suppose, build up domains of inquiry. Because I suppose like part of, I don't usually know how the research group works, but I guess we need some structured approach to exploring the problem space. And I guess like part of that is figuring out what questions do we want to, what questions are we trying to ask, and what is the scope of the work?
Yeah, so of course the research group is called a research group, but it's not doing research. It's trying to encourage people to do research and taking in that research and so on. But somebody must be there to actually do the research, and having a good description of these domains of inquiry, to borrow your term, is definitely a good way to foster research. Ellen.
So this might be out of scope for this research group, but one of the things that we would be very interested in is to have a better understanding of, for the physical interfaces like USB, like I2C, what kind of granularity makes sense there. For USB, for example, our current API basically allows a runtime to give a workload access to a single USB client device. Does it make sense? Because there's an entire tree inside of that client device. Does it make sense to go smaller and say like, oh, this only gets access to specific nodes of the client device or specific operations? I don't think we have the required expertise in terms of, does it actually make sense to become smaller?
Yeah, I think the interesting question here is, since nobody has anything that provides isolation on the software side, people are unlikely to have built hardware or even deployed hardware that makes use of that. So this may be a case where having the functionality will actually seed the projects that can make good use of it. Kerry.
I think there's sort of a model for that in VM environments like VMware. So, for example, if you plug in a USB device, it'll ask you, should this remain with the host? Should it belong to the VM? But I think even in that case, it doesn't really address multi-tenancy. But maybe something could be built on that paradigm. It's usually useful to build on something that people are familiar with. For user comfort, I think, as Carolina was talking about.
So Karina is at the head of the queue, and Emmanuel just came up. So
yes, I just wanted to say, so actually the granularity part was like a thing that I found very interesting when reading your paper, because I think it opens a very interesting set of like issues about about the security model. And also there's a lot of questions of like flexibility versus overhead, because so if you're dividing control policy or even firmware into containers, like where do you stop? What is the granularity of like how you divide the firmware up into little pieces, and when does it provide like when is the overhead too much, or the complexity of interfaces into design for that too much to be worth the effort? So I think that's a very interesting field of inquiry, personally.
okay, Emmanuel, you wanted to say something?
Yeah, so it's just a side comment, and actually, I guess that's part of the reason why I'm sitting in this meeting. So we had some prior work that we had published a couple of years ago on actually an alternative to using WebAssembly that is like way smaller. So it's a different approach, obviously, in terms of isolation. It has provides like less aspects like that, but still, like we've been using eBPF adapted to microcontrollers to actually do essentially what we're talking about right now, and did some work on providing some proofs on how the memory is isolated for fault isolation for the actually the the hosting engine, and we have some code for that that we published also for Riot. So depending on like the sense of like how WebAssembly being the consensus as a base or not is, then you know this might come into scope to be considered or not. What I get from interaction with various people is that you know WebAssembly is very attractive, and I mean it's great. Like, but there's a penalty to pay in terms of like the size of the components you'll have, and there's a you know you can't expect something like so small. So as soon as you're having a lot of components in mind, then there's only so much you can have like running in parallel on your device, right? So one way to, yeah, so we'd have to look at what's in scope here in terms of like scalability at that level.
So on the chat, you ask whether we have a consensus on WASM. I hope we don't, because I would be really interested in looking at comparisons here. So people have been defining IoT virtual machines for a long time. So Dave Cutler has a paper from 2002 describing one, and that kind of worked. When we worked on this in 2017 or so, our main problem was you need all the tooling. And it doesn't make sense to have a virtual machine where you cannot program for. What WASM brings is existing tooling plus a lot of energy in actually creating additional tooling as required. Well, eBPF is certainly also an area where tooling exists and is being worked on. So maybe these are the two proposals that actually make sense to compare. Maybe there is a hierarchy here that you can put up simple things with eBPF and more complex things with WASM. So that might be a research question for someone to look at. So looking at the clock, we are already 3 minutes out of our envelope here. So if somebody has a last question or a last observation they want to get rid of, I would like to hear it. Otherwise, many thanks to the presenters for preparing these talks and letting us have a little bit of share of their work. And I think this subject here is definitely interesting enough that we will continue looking at it in the Think Your Thing research group and define our domains of inquiry that we want to push forward. And I'm looking forward to having all of you contribute to that.
Thanks for proposing this topic.
Well, Carolina proposed it originally, so she gets those flowers.
Yeah, thanks, Carolina,
Okay.
for pulling us into this.
Thank you for everyone for listening and having lots of good questions and ideas.
Okay. So see you around in MeetAgo probably, or some other tool. Unless you go to Montreal, then we can actually meet physically. Talk to you then. Bye-bye.
Thank you. Bye-bye.
Bye, everyone.
Thank you. Bye.